All right, let's dive right into this explainer and see if we can solve the ultimate playground mystery. Basically, what exactly makes things move in our universe? Whether you're kicking a football, throwing a stone up in the air, or just watching a gentle breeze make the tree branches swing, there is some serious, fundamental science behind all of it. Today, we're going to explore the incredible laws of motion. We're going to act as physics detectives to figure out the invisible forces that govern literally every single jump, throw, and crash around us.
Have you ever actually stopped to wonder what invisible rules control all that everyday movement? Let's start with a really simple definition based on what we see all the time. To move a football that's just sitting there, someone has to kick it, right? Or to stop a ball rolling down a ramp, you have to push against it. Well, these everyday pushes and pulls are what we call forces. They act as an external agency. You can think of a force as this invisible hand that's absolutely required to put a stationary body into motion, or to stop a moving body in its tracks. And here's the wild part. Sometimes this external agency doesn't even need to touch the object. Think about how gravity pulls a stone falling from a tall building, or how a magnet can pull an iron nail from all the way across a table.
So let's kick things off with Section 1, the Great Physics Mistake.
For a remarkably long time, humanity actually had the basic rules of movement completely wrong. Let's look at the misguided detective of our story. He was a highly famous ancient Greek thinker named Aristotle. He observed how the world worked and concluded that an external force is always required to keep a body in motion. And honestly, think about it. If a small child is playing with a non-electric toy car on the living room floor, they know intuitively that they have to constantly drag the string to keep the car going. The second they let go, the car stops. So Aristotle's idea made perfect sense at the time. But centuries later, Galileo realized there was an invisible culprit hiding right in plain sight that was actually causing that toy car to stop.
To figure out the true laws of nature, Galileo knew he had to imagine a perfect world, a world with absolutely zero opposing forces. He ran experiments using an inclined plane, which is basically just a ramp. He noticed that objects moving down a ramp accelerate, while objects moving up a ramp slow down, or retard. So he reasoned that motion on a perfectly horizontal plane must be right in the middle. It shouldn't accelerate and it shouldn't slow down. He realized that on a perfectly smooth, frictionless surface, if a ball was rolling on a flat plane, its motion would literally never cease. It would just keep going forever. No continuous pushing required.
Which brings us perfectly to our next segment, Rule 1, the laziness law.
Galileo's brilliant insight completely dethroned Aristotle's old ideas, and then Sir Isaac Newton came along and took those discoveries to build our modern rules of motion. He created 3 famous rules, starting with his first law of motion. To really feel this rule in your bones, picture this. Why do we jerk backward when a stationary bus suddenly starts moving? Well, your feet are touching the floor, so friction pulls them forward along with the bus. But the rest of your body? It wants to stay exactly where it was. Your body is literally resisting the change in movement, leaving you feeling like you're being thrown backwards until your muscles quickly correct it. So, the absolute crucial takeaway here is that objects are fundamentally lazy. We call this property inertia, which literally translates to a resistance to change. Newton's first law states that a body continues to be in its state of rest or of uniform motion in a straight line unless it's compelled by some external force to act otherwise. Just imagine a spaceship out in deep interstellar space, super far from any planets, with all its rockets totally turned off. Because there's no net external force acting on it out there, it will just keep drifting with uniform velocity forever. It won't stop and it won't speed up. Why? Because objects just want to keep doing exactly what they're already doing.
Moving right along, let's look at Rule 2, force and momentum.
So what happens when our spaceship isn't just drifting? What happens when we actually fire up those rockets? We're applying a net external force to change how an object is moving. To really grasp this, we have to look at a concept called momentum, which simply combines an object's mass with its velocity. Think of it like this. If a small, lightweight car and a heavily loaded delivery truck are parked on a road, which one is harder to push to get up to speed? The heavy truck, obviously. It takes way more force. And if they're both rolling towards you at the exact same speed, that heavy truck is going to need a much greater opposing force to safely stop. That unique combination of mass and speed is momentum. Newton realized that if you apply the exact same force for the exact same amount of time, you'll cause the same change in momentum, no matter how big or small the body is.
And this brings us to what is probably the most famous equation in physics, Newton's second law. Force equals mass times acceleration, or F equals ma. It tells us that force is directly tied to how quickly momentum changes. Consider a cricketer trying to catch a fast-moving ball. If they just hold their hands completely stiff, the ball stops instantly. That abrupt stop applies a massive, painful force to their hands. But by pulling their hands back as they catch it, they increase the time it takes to stop the ball. This spreads out the rate of change in momentum, drastically reducing the force on their hands. It's a real game changer. Acceleration here and now is determined entirely by the force applied here and now.
Okay, that leads us right into our third rule, action and reaction. Now that we know how force creates acceleration, we have to ask, where does it even come from? Well, Newton discovered a pretty mind-blowing secret about this. Force never ever occurs singly in nature. Force is actually the mutual interaction between two bodies. What this means is that you literally cannot touch something without it touching you right back. Every single time an external force is applied, it arises because of another body, instantly creating an equal and opposite reaction. It is a completely mutual relationship. Imagine you're pressing your hand down hard on a coiled spring. That right there is the action. But you can actually feel the spring fighting back against you. The reaction is that compressed spring pushing back up against your hand with the exact same amount of force. It's the exact same science that powers a rocket launch. The massive engines push a huge amount of hot gas downwards. That's the action. And the gas pushes the rocket right back up into space, which is the reaction. Here's a crazy one. Just like when gravity pulls a falling stone down to the Earth, the stone is actually pulling the massive Earth right back up toward it with an equal and opposite force. We just don't notice it because the Earth is so incredibly massive that its acceleration is essentially zero.
Finally, let's look at Section 4, friction, friend or foe.
So, we've successfully cracked the case of inertia, momentum, and action-reaction pairs. Now, let's unmask the identity of the invisible force field that originally tricked Aristotle all those centuries ago. This force is constantly present in our natural world, acting on solids and fluids alike. We're talking, of course, about friction. Friction really is a master of disguise. On the nuisance side of things, it's the annoying opposing force that wears down the soles of our sneakers and grinds down moving machine parts over time. It's exactly what makes the toy car stop on the living room floor, which tricked Aristotle into thinking forces are needed just to maintain speed. But on the hero side, we literally couldn't function without it. Friction is what grips our feet to the floor of a moving bus so we don't instantly slide to the back when it accelerates. It's the only external force along a smooth road that allows a car's tires to actually grip the pavement and push the car forward.
So friction, gravity, pushes, and pulls, these are the essential tools that build the motion of our entire universe. To wrap up this explainer, I want to leave you with a bit of a thought experiment. If the hero and nuisance of friction completely disappeared tomorrow, turning the whole world into a perfectly smooth ice slab, how on earth would you use Newton's invisible rules of momentum and action-reaction to walk, drive, or even stop yourself from drifting forever? Keep observing the incredible physics acting all around you, because once you look closely, you'll see these laws in every single move you make.